Let's see if that's positioned okay. Yep. All right. Number one. Which of the following is an example of a quantitative observation? Remember, think when you see quantitatives, think quantity, numbers. So look for something that has a number associated with it. And it looks to me like the only one that works is D. Liquid is 60 degrees Celsius. The rest of them are just comparisons or what we call qualitative or descriptive terms, right? Two, generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called, it's a natural law. It's a law. By the way, a lot of my questions are multiple choice. So when you're taking a multiple choice test, and you're presented with only a certain number of answers, give the best answer. If you think it's not in the list and you don't have the option of saying none of the above, then go for the best answer. And the best answer here is natural law. Okay, how about this one? Oh, this does require some memorization also. I forgot about this. Prefixes for units of measure. So of these four prefixes, order them from smallest to largest. Right, if we take, let's see, I'm going to go through here and pick out, there's some repetition and there's some not. So let's say this is number 5. Let's see, we have nano. We have milli. We have centi. We have kilo. Let's see, milli, nano, centi, kilo, milli, centi, nano. Oh, that's it. That's just those 4. Okay. If you're going to put them in order of smallest to largest, what we mean is the one that makes a small, makes the unit the smallest. In other words, when we put, say, milli in front of a unit, it reduces the size of the unit by a factor of 1,000, or 10 to the minus third. Centi reduces it by 10 to the minus 2. Kilo increases it by 1,000, 10 to the third. And nano reduces it by 10 to the minus ninth. Right? So, as written, that's the correct order. This is smaller than that one, is smaller than that one, is smaller than that one. Okay? And you have to know what those units mean in order to answer this question. All right, number 6. Let's see. Let's see if this will work. I have to do this first. And then wipe off the shadow. Okay. See if I'm still centered. Okay. 8.1 kilograms contains this many grams. So 8.1 kilograms, and we want to make it into grams. So we need a conversion factor that will go from kilograms to grams. Okay. That's the unit we want to end up at. So it has to be in the numerator. And the one we want to cancel has to be in the denominator. Because this is the numerator, that's the denominator. We need to cancel those. Now we need the relationship between grams and kilograms. So 1 kilogram is 1,000 grams. Right? So if you look at the answers, some of them are standard notation and some of them are scientific notation. So I would go for scientific first, 10 to the third, and see if it's there. And it is, it's B. If it wasn't there, then I would go to standard notation, and that would simply mean 8, 1, let's see, 3 places to the right. 1, 2, 3. Like that. But remember, we can't put a decimal there because this only has 2 significant figures. So we have to leave that decimal out. These 2 zeros are not significant. That's 2 significant figures, and it would be 8100, but that's not there. But if this weren't there, that's the way you would go. Standard notation and see if it's there. All right, 7. Convert 0.3980. 0.3980 what? Meters. We want to go to millimeters. Now, I've had students that learned, I guess it was in high school, learned conversions by using that picket fence, right? They do like this, and they go like that, that, and that. And that's fine. Numerator, denominator, it works. I just like this. Okay, we want to go to millimeters, so that has to be up here and meters down here. So how many millimeters in a meter or how many meters in a millimeter? It works either way. Let's do it this way. 1 millimeter is 1,000th of a meter, 10 to the minus 3 meters. So in this case, you would divide by 10 to the minus 3, which is the same as multiplying by 10 to the third, correct? So we would get 1.3980 times 10 to the third, and then convert that to scientific notation. Notice I took one of these powers of 10, multiplied 10 times this, which brought the decimal over here. Does that clear? Okay. And let's see if that one's there. Let's see, 3.980 times 10 squared. No, it's not there. So we go to standard notation. So I take the rest of this, which is 100, which will be there, be 398.0 millimeters. And our answer is A. Now, the only way you're going to get comfortable with this type of stuff, this unit conversions, dimensional analysis, is to work lots of problems. I mean, just have them coming out of your ears. Okay, number 9. Looks like a logic question or a definition. What's the measure of the resistance an object has to change in its state of motion? Now, I didn't present it that way in class, I don't think. But this is a measure of mass. In fact, that is the actual scientific definition. We say that mass is a measure of substance, but how do we know? We know because of Newton's first law. An object in motion tends to remain in motion unless acted upon by an external force. An object at rest tends to remain at rest unless acted upon by an external force. So that's that resistance part that we're talking about here. It resists changes in its motion, and that's a measure of mass. Okay? All right, number 11. As part of the calibration of new laboratory balance, a 1 gram mass is weighed with the following results. And there they are. And I'll explain what those measurements mean in just a second. First of all, I want to point out that we're using a standard mass. of 1.000 grams. In other words, that's the accepted value, or that's the true value of the mass, 1 gram. All right, we call that the true value. Now, when we make 3 measurements, we get 1.201, 202, 200, plus or minus 0.001. That plus or minus is derived from standardizing the balance itself. So we know that the accuracy of the balance is good at the 3rd decimal point, plus or minus 1,000th of a gram or 1 milligram. But when we use the balance, we find that it's telling us 1.201, 202, 200. So is it accurate or not accurate? It's not accurate by a long shot, right? If you take 0.2 and ratio it to 1, that's 20% error. Right? That's a huge error. So it's not accurate. But the other question is it precise? Yeah, are the measurements precise? And the answer is yes, because they're within actually 0.002, which is not too bad, of each other. So they're tightly grouped, but they're just off target. So the values measured are precise. Now, the question doesn't ask this, but I want to interject this while we're here. The error here is in the accuracy, but it's the same, almost the same error every time because the measurements are precise. So that means that it's the same error every time, which is a systematic error. In other words, something in that balance is causing it to go off that much every time, which means all we have to do is correct that discrepancy. And a good technician can do that with your balance and bring it back down to 1. Okay? So systematic errors can be corrected. Most of them can be corrected readily. Random errors cannot be corrected because we have no idea the source of the error. So random error would be if your values were like 1.2 and 1.5 and 0.9. Those would be just wildly imprecise, and we couldn't correct for them. You just toss the balance and buy a new one. Okay, that was 11. Let's move down. We're still talking accuracy and precision. Let's see, and we're going to use these diagrams and go through 13. Yes, just through 13. So we can leave it just like that. So we got 12 and 13. 12 says, which of the following figures, actually not which of the following, which of the previous figures, there's a correction required, represents a result having high precision. Okay? Precision means grouping. So which ones have tight groupings? Roman numeral 2, Roman numeral 3, both. So that's why E is the correct answer for 12. Number 13 says, which of the following statements concerning these figures is correct? So we have to read each one. We don't have any. Sometimes multiple choices will have some squirrely answers, like none of the above, 2 of the above, all the above, that type of thing. If that's the case, then you're going to have to look at each one of the answers. If they're all unique answers, then we can go down through them, and when we find the correct answer, we can stop. You can save yourself some time on an exam. If you know the material well enough, then you can do it that way. If you don't, and you're going to have to narrow it down to two and take a guess, which happens sometimes, then you'll have to look at all of them. But A says figure 1 represents a systematic error. No, number 1 is random. It's completely random. So A is out. B says figure 1 represents a random error. Yes. And figure 2 represents a systematic error. That's true. B is true. Now, since we don't have any that says 2 of the above are true or none of the above are true, then we found our answer, B. If you look at the others, you'll find that they are not true. Figure 1 and figure 2 represent random error? No, only figure 1. D says figure 1 and figure 2 represent systematic error. No, only 2 does. And figure 3 represents no errors. It does represent error. It's just very small error. Notice that those shots that were taken against this target do not all hit the bullseye. Right? There's some error. So E is also false. That means B is our best answer. And 16. See, that was running out of ink. Um, 16 says the amount of uncertainty in a measured quantity is determined by. I think I mentioned this in class. The uncertainty in a measurement is dependent upon two things. One is the accuracy, the reliability, the precision of the instrument, and the skill of the operator. I've seen instruments that were kind of marginal in their ability to produce a good answer, and a skilled technician comes in and gets amazing results out of that machine. And I've seen it go the other way too. You pay $250,000 for an inductively coupled argon plasma spectrometer, and bring in a technician that doesn't know which way is up, and you're going to get garbage out of that instrument. So you got to have both going for you. I would rather have the skilled technician and the marginal instrument, but the ability of both is comes into play. So that means A, both the skill of the observer and the limitations of the instrument are at play here. 17. A scientist obtains the number 0.045, 0.0, yeah, 450067 and 00. Calculator spits that number out. If this number actually has 4 significant figures, how should it be written? Okay, you've got zeros here. We know that non-zero numbers are all significant. And we've got 3 types of zeros here: left, bracketed, and right. So we got to decide which ones are significant. These are not significant. These are significant. And these, because there's a decimal right there, these are also significant. So we need 4 significant figures. That means we don't start counting significance until we get to the first significant number. Now we can count. So we're going to have this one, this one, this one, and that position. So this position dictates that we go here and see, is it greater than 5? Yes, it is. So we write the number like this: 04501. That's 4 significant figures. And that makes E the answer. All right. Number 17. No, I did that one already. Scrolled. There we go. Number 20. Okay, express the number in scientific notation. 0.08190. 0.0810. To do scientific notation, of course, the coefficient has to be between 1 and 10, and we have to preserve the number of significant figures in the coefficient. In addition to moving value from the number into the power of 10. So, how many significant figures do we have here? We have 3. That means we need to keep this one like that, but where did the decimal go? Well, it goes 1, 2. That means, since we move to the right, we're storing up negative numbers. 8.10 times 10 to the minus 2. So that's D. Okay. Uh, 21. Let's see. Express the number in common decimal form. So we're going from scientific to standard notation. 6.49 times 10 to the minus 3. So if we've got a negative power of 10, that means the decimal has to move which direction? That way. Got to make this number smaller because that's a negative power. So it has to move to the left. And it has to move 3 places. So I would write 649. Give myself some zeros out here. Doesn't matter how many. And we go 1, 2, 3. There's your number. Number 22. Express the number 2.37 times 10 to the fourth in standard notation. So with this one, we have a positive power of 10. 2.37 times 10 to the fourth, was it? Yep. So for this one, if we write it in standard notation, that means the number has to get bigger because this is a positive power of 10. So we go 2, 3, 7, give ourselves some zeros, and move 1, 2, 3, 4. That's a placeholder. The reason I put that there was just to be sure I erased the right number of zeros, but it only has 3 significant figures in the number, so I can't put the decimal there. That leaves only 3 significant figures in accordance with, in agreement with scientific notation. Okay, so the answer is D, 23,700, with only these 3 significant figures. All right, 23. We generally report a measurement by recording all the certain digits plus how many uncertain digits. That's just memory, right? 1. Okay. And the uncertain digit is the farthest one to the right. The furthest significant digit to the right. Let's use that previous problem. 23700. When we write it this way, we're saying that these are significant. That means this is uncertain. And these are certain. We can't say that that one's certain because it's not significant. So this is our uncertain digit. These are certain digits. And these don't count. All right. 24. You're asked to determine the perimeter of a cover of your textbook. You measure the length as sometimes it's solve a problem. You need to draw a picture. So I'm going to draw the textbook cover. Okay. It's 39.36 centimeters long. Okay. And it's 24.83 centimeters wide. All right. Now, you measure the length as such and the width as such. How many significant figures should report for the perimeter? So what is the perimeter? The perimeter is this plus this plus this plus this. Okay. So this is significant figures of an addition. Right? We only use addition rules in this case. Right? So what we would do is put 39.36, 39.36, 24.83, 24.83. See. I like to do calculations in manually sometimes just to keep my mind active. So let's see, that's 12. Let's see, that's 18, right? 6, 6, 6 is 18. 1, that's 3, 6, 7, 15, 23. 2, 11, 20, 28, and 2. That's 6, 6, 8, 10, 12. Okay, so we get that position. We can keep everything down below because there's our limiting. They're all the same number of decimal points. So we have 5 significant figures in our answer. That's why E is the answer. The temptation is to use the multiply divide rule for this one and say they're only 4, but they're not. Right? The add subtract rule says there are 5. All right, 25. See, am I still on screen? It's drifting a little bit. Consider the numbers 2368 and 4.12. The sum of these numbers has so many significant figures, and the product has so many significant figures. Okay, the product is easy. Right? It's going to be the least number. So 2368, 2368, and then 4.12. Yes. This is the one that's going to be iffy. So we have 3 significant figures here. The product is going to be 3 significant figures. So it's either A or D. All right. We have to decide what is the sum. Is that right? Number says, yeah, the sum. Okay, so that's 1, 7, 8. That's 7. That's 2. So it has 4 significant figures. So the answer is D. 4 for the sum, 3 for the product. 27. Using the rules of significant figures, calculate the following. 40021 minus 0.179, 0.179. So you just do it like your calculator would the first time, and then you decide how many you can keep. So let's see, 0 from 1 is 1, that's 3, 7 from 9 is 2, 1 from 9 is 8, and that's 3. So we can't keep this one, right? Because we're limited to that decimal place. So we can only say 3.823. Here's the problem. If we write it in standard notation, oh no, we can't keep that one. There's not a problem. My mistake. right? We just throw that one out because it's less than 5. Okay, did I confuse anybody? Bring them all down, but we can't keep that one, right? So uh, that's less than 5. We keep the 3, and we just throw that one out. Now we have 3.823 is our correct answer. Okay, here's a combination calculation. In number 32. Let's see. So we have 3.478. 3.478 times 1.164. 1.164. And the units of measure for that calculation would be grams. And then we divide it by 2 milliliters. And then we subtract 0.169. 169 grams per milliliter. Okay. It's important when you're actually doing an experiment, when you're making these measurements, to make sure if you're going to subtract two numbers from each other, that they have the same units of measure. And this is grams divided by milliliters, grams divided by milliliters. We're good. And now we have to do the calculations. So, everybody remember what this means? That's the order of calculation. Parentheses. So you do the parentheses first. Then exponents if you have them. Multiply if you have them. Of course, we have multiply here, but it's in the parentheses. Then divide. Then you add or subtract. Okay, so we're going to do this first, divide by that, then subtract. Well, this multiply and divide, they go by the same rule. So we can do this divided by that and then decide how many significant figures to keep. So I'm going to use my calculator on this one. 3.478 times 1.164 and divide by 2. My calculator says 2.024196. Okay, so how many can I keep? The least number in the operators. 443. So I can keep 2.02 because that's a 4. Then that goes out and I keep that. Now I want to subtract. I'll just put it up here. 2.02. Okay. So now 9 from 10 is 1. 6 from 11 is 5. 1 from 9 is 8. And 0 from 1 is 1. So we check ourselves, right? The 10, 1, this is 11, 12, 1, 9, 10, 1, okay, that's good. Now, how many can we keep? There. That's 1, so we keep 1.85. That's our answer. Let's see, we still only have 1, 2, 3, 4. Okay. Now, 35. There we go. It's still on screen. 35. Express the volume 781.2 cubic centimeters in liters. All right. 781.2. 0.2 cubic centimeters. And we want liter. Okay. What's the conversion factor? Well, The easiest way to do this is to recognize that a cubic centimeter is exactly the same as a milliliter. Now we can make the conversion. Milliliter is in the numerator. Here it's in the denominator. There. How many milliliters in a liter? 10 to the third. Right? 10 to the third milliliters. So we're going to divide by 1,000, which means tens, hundreds, thousands. That's 0.7812 liters. Number 37. Okay. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. What is the pressure when expressed in grams per square meter? 14.7 pounds per square inch, pounds per square inch. Okay. This is going to be a chained conversion because I don't have a conversion factor in my head or in useful information that will go from pounds per square inch to grams per square meter. So we're given some conversion factors there, and I'm going to show you how to chain them together. When you got a quotient or you have a unit of measure that has more than one part to it, then do one unit at a time. So we're going to take pounds and go to grams first. All right, pounds. Now, do we have a conversion to go to pounds to grams? No, we have one to go to kilograms. But that gets us in the correct system, in the metric system. So let's do 2.205 pounds per 1 kilogram, right? Now we're going to go from kilograms to grams. And then the third. Okay, grams, we're good with grams. Now, let's take care of square inches. Conversion factor here is 1 inch is 2.54 centimeters. So, inches on top, right? Because inches are on the bottom here. And centimeters here, 2.54 centimeters. Okay, what's wrong with that picture? They're not squared. So here's what you do. Square the whole thing. That squares this one and it squares that one. And now we have inches squared and centimeters squared with whatever 2.54 squared is. That gives you a proper conversion factor. Now we're in square centimeters. We need to go to square meters. Right? Centimeters up here, meters down here. We have 100 centimeters in a meter, but we're not squared yet. So do that. So that squares this one, which cancels that one. That squares inches, which cancels inches. And we get square meters out of this calculation. Okay, is everybody following me so far? Circular nods. Okay. That's the thinking part of the problem. The rest is number crunching. So how do I crunch numbers here? I go across here, multiply, 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 take that same number, the result of that, divide, 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 divide. Right? So with an algebraic calculator, you have to say something times this one, and then times this one, and then times this one, times this one, and then divide this one, divide this one. With my calculator, which is a reverse Polish notation, what I say is 14.7, and then that's 1, Then I say 1,000, and then I tell it what to do with it, times it. And then I go over here, 10 squared, 10 squared squared is 10 to the fourth, right? Which is 10,000. Okay, so I got the top row done. Now I go to the bottom row and divide by 2.205 and divide by 2.54 squared. I find my square button, there it is. And then divide. So I get 1.03. Let's see. These are conversion factors, which means they're exact numbers. So the only limiting factor to the uh, significant figures is this one, which has 3. So I say 1.03 times 10 to the 7th. I rounded what my calculator gave me. Now, let's see. Yeah, 1.03, 10 to the 7th is B. There it is. Sometimes I work these problems and the answer's not there. It's because I made a mistake. Simple conversion factors are hard enough for students to grasp the concept if they've never seen it before. These chain conversions seem very complex, but they're not really. They're just simple steps chained together. Okay, I got 15 more minutes. Let's see how far I can get. 41. Let me see. We've got what amount of time in the lab? We've got an hour and 50 minutes in the lab. If I go over just a little bit, it shouldn't impact our lab experience that much. 41. The density of liquid mercury is 13.6 grams per mil. Okay. And we want to express that in pounds per cubic inch. Right. This is another chain conversion. So 1 unit at a time, I'm going to take grams to pounds first. So we're going to say grams to kilograms. Right? 10 to the third grams per kilogram. Now I'm going to take kilograms to pounds. Two point oh, no, 2.205, excuse me. 2.205. There we go. Now we got the numerator fixed, pounds. Now we want to go to cubic inches. So we've got a milliliter here. We know that a milliliter is a cubic centimeter. So now we can change centimeters to inches. 1 inch is 2.54 centimeters, and cubit. And that puts us in the realm of pounds per cubic inch. Pounds per cubic inch. Is that where we're headed? Yes.
I have
Okay.
a question.
Yes.
So I guess you showed how to use the ladder method earlier. Um, so in this scenario, when you go from the pounds over kilograms, and then your next step is the centimeters over the inch there towards the end, does it
Yeah.
not have to be like it doesn't have to cancel out kilograms next? Like, how did you get from centimeters to inches
Oh,
after that?
okay. I'm taking 1 unit at a time. So I resolved the pounds, the grams into pounds first. That's what this part does.
Okay.
This part resolves the milliliters or cubic centimeters into cubic inches. And since we're multiplying and dividing, you can put these factors anywhere. It
And
doesn't
it
matter
doesn't,
where,
yeah.
yeah, it
Okay.
doesn't matter where they go. I mean, you
So
can do this.
anytime you resolve the one unit, you can immediately just start throwing in the other unit.
Yeah. Once you get to
Okay.
that point, then you can go to the next one.
Okay.
Yeah.
Cool.
The only thing, and maybe that's why some students use that picket fence method. That way, it's a single line and dividers, and you put things in there like that. If that makes more sense to you, then by all means use it. So we just have to resolve that. And in the interest of time, it should work out to 4.91 times 10 to the minus first pounds per square inch. Pounds per cubic inch, excuse me. Pounds per cubic inch. Should be answer B. Okay, 46. All right, during a physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? All right. So you're given the speed of light there, 3 times 10 to the 8th meters per second, and you're given a conversion factor from kilometers to miles. So we're going 93% of the speed of light. So the speed of light is 10 to the 8th meters per second. But we only want 93% of that. And I'm using the decimal equivalent of 93%. We could write 93 over 100, like 93 parts per 100 parts, and it would give you the same answer. But I'd like to use the decimal. So this is our starting point. Now we're going to change that to miles per hour. Okay. So we'll take meters and go to kilometers. 10 to the third meters per kilometer. Now we'll convert kilometers to miles. Right? So the conversion factor is 6214. 0.6214 1 kilometer. Okay, that takes care of that factor. Now we're going to do the time factor. So I'm come around over here, and we want hours in the bottom, seconds in the top. How many seconds in an hour?
3,600.
Yes, 60 in a minute, 60 minutes in an hour, 60 times 60 is 3,600. That's exactly right. That gets rid of denominator, numerator, and hours in the denominator as we want. Okay, then we just multiply those all out. All right, that's the thinking part. Multiply them all out. We should get 6.2 times 10 to the 8 miles per hour. While we're here, and let's see, that's E. While we're here, notice that the difference in size of the kilometer versus the mile. So which of these units is longer, the mile or the kilometer?
Would would it be the kilometer?
Nope,
No.
it's the other way around. Yeah.
Okay.
If the number gets smaller, the unit gets bigger. Okay. Or you can think of it this way. If I travel 1 kilometer, how many miles did I go? I only went 6/10 of a mile, right? I haven't even gone a mile yet. You can think of it that way. Okay, 49. Excuse me. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of the ore molybdenite. The percent by mass of this element in the ore was. The one guess what element it is. If the mineral is molybdenite, the element has to be molybdenum, right? So we want to calculate the percent by mass, which is simply if the total mass is 660 kilograms and the element isolated is 29.3 grams, we've got a unit conflict there. In order to do percent, the units must be equal. So you can take your pick. You can convert grams to kilograms or kilograms to grams. I like kilograms to grams. So 29.3 grams of the element molybdenum in 660 kilograms. Here's what I would do. 660 kilograms. And then what does kilo mean? Kilo means 1,000. So I would simply do this. There's my kilo right there. Okay? And that gives me grams times 100. Now, in the interest of time, I should come out with 0.004444%. Very small amount. So I think we could say molybdenum safely. We can say molybdenum is a rare element. My hope is that there are a lot of other different elements that can be isolated from that ore also. They don't have to throw away, almost 660 kilograms of ore just to get that much element. Probably most of these metal elements, the transition metals, they occur in groups. So once they isolate those from the ore, then they can separate them into molybdenum and whatever else is with it. So it's not a total waste. All right, 50. Okay. Okay. 409 Kelvin equals what? Notice that the answers are in degrees Fahrenheit and degrees centigrade, or Celsius, excuse me. So I would convert Kelvin to Celsius and see if one of those answers is the right one. If it's not, then I would take Celsius to Fahrenheit and see which one of the other Fahrenheits it belongs to. So 409 Kelvin, remember Kelvin equals Celsius plus 273. So if we want Celsius, we have Kelvin minus 273. So Kelvin is 409, right? 409, that's 631, 130, yeah, 136 degrees C. Is that one of them? Yep, D. Now for 51, we actually do have to convert Celsius to Fahrenheit. '51. And we're going from 391 degrees C to degrees Fahrenheit. So the formula for that conversion is in useful information, which means it will also be available for the exam. But if you use it enough, you'll memorize it anyway. We want to go to this one So the way I memorize the formula is the way we're going to use it. Equals 9/5 C plus 32. Right? So we put 9/5 times 391 plus 32, and that's equal to degrees Fahrenheit. And if you work it out, it should be 736 degrees Fahrenheit. Now, I think I mentioned during the last, the only class we met, that um, a good skill to develop is one of estimation. Okay. You don't have to get the exact number. You just estimate the answer so you can see if your exact calculation is reasonable. Well, one of the things I like to do is you drive by these banks and they have the temperature listed up there, and it'll cycle through. It'll give you the time, maybe the date. It'll give you the temperature in Fahrenheit, and then it'll switch and give you the temperature in Celsius. Um, if it gives me the temperature in Celsius and I want to know what Fahrenheit is, then I know a relationship that 20 degrees Celsius equals 68 degrees Fahrenheit. And the ratio of centigrade to Fahrenheit, after we get to this point, we've already taken into account the 32 correction factor. So now all we have to do is take the 9/5. So the 9/5 says that if I increase this one by 5 degrees, I increase this one by 9/5. So this would be 77 degrees Fahrenheit. If I decrease it by 5, then I decrease this one by 9, which would be 59 degrees Fahrenheit. So I can estimate the temperature while I'm driving my car. You don't want to take your eyes off the road too long. So once I see that, then I can put my eyes back on the road and make the conversion. If it's in between there, I just sort of estimate, interpolate, we call it. Okay, 54. 1984, some drums of uranium hexafluoride. Uranium hexafluoride were lost in the English Channel. You know what? There are, let me back up. When we name compounds, they're generally subdivided into one of two groups. A systematic name is one that follows the rules set out by IUPAC, International Union of Pure and Applied Chemists. If it's not following those rules, then we call it a trivial name. And uranium hexafluoride is a trivial name. It tells us what to do, but uranium is a metal with multiple charges possible. Let's see. What are they? Plus 3, 4, 5, and 6, right? So, um, we're actually naming that one with the type 3 compound convention, hexafluoride. What we should be doing is the proper name for this would actually be uranium. Uranium. All right. Yeah. Uranium 6 fluoride. Because uranium has multiple possible charges, fluoride only has a -1. So if we have 6 of them, that means this has to be balanced with a +6. This is a type 2 convention. This is the systematic name. Uranium hexafluoride is a trivial name. Okay. All right. Now let's get back to the problem. And that's characteristic of all type 2 compounds. You have to specify the charge of the metal with Roman numerals. Okay. The water in the English Channel is cold, 17 degrees Celsius. So you don't want to be in that for very long, even in the summer. The melting point of uranium hexafluoride is 148 degrees Fahrenheit. In what physical state is the uranium hexafluoride in these? The idea here is to convert Fahrenheit to Celsius. Right? So if this is the formula that I memorized and I solve for C, then I would put, let's do it this way. First, I would take this over here. Then I would multiply both sides through by 5/9, right? Times 5/9 times 5/9. That would get rid of this and leave me with C. So C equals 5, let's see, 5/9, and that's the whole thing, times F minus 32. So I would say Fahrenheit minus 32. 148 minus 32 is 116. 116 times 5/9, which is about a half. Right? It's a little actually it's a little more than a half. So half of this would be 58. And more than that would be, it's closer to 60. It's about 60 degrees. And that's good enough to answer the question. Because the temperature is 17 point. That doesn't make a whole lot of sense, does it? Yeah, it does. This is uranium hexafluoride. Okay. I'll explain that head smack in a minute. 60 degrees is greater than 17 degrees, so the uranium hexafluoride is solid. The head smack was for recognizing that uranium metal has a very high melting point, but uranium fluoride has a reasonable melting point, 60 degrees Celsius. The reason that's important is for purification purposes. We convert uranium into fluoride so that we can get it into the gas phase. At this temperature, it's liquid. We heat it some more, get it into the gas phase. Now we can put it through a purification process, a separation process, so that we can separate the U-235 from the U-238 and concentrate the 235, which is the fissionable material. If we get it up to 3 or 4%, I think that's good enough for nuclear reactors. But we got to get it up to 95% to be a bomb. And that's where Iran is headed. They want to make a bomb worse than I want $1 million. So I'll let it go at that. 56, number 56. Let's see. I'll read it from up there. I got something covering mine up. So this is an interesting problem, and it requires that you understand some things about geometry. A monolayer. What's a monolayer? One layer, yeah. It's a layer of molecules, in this case, that are oriented so that this is oleic acid, which has a a long string of carbons that make it non-polar on that end. That is hydrophobic, doesn't like water. And then you've got the end over here with your carboxylic acid group. That's water loving. That's how soap works. Soap has a water loving side and a grease loving side. So when you use soap on your clothes, and we don't do that anymore because of the scum problem, but the theory is the same. This dissolves in water and that dissolves in the grease, and that bridges the gap, and that's how you get grease out of your clothes. Well, in this case, we've got oleic acid, which has been spread on the surface of water. And it spread out to this diameter. So there's more water out there. Now, how do I know that it spread that out? I just blew talc, some real fine powder on the surface of the water. So when I put the drop of oleic acid on there, you can see it move. So we got the diameter here, which is, well, it gives us the area, 20 cubic square centimeters. So the area is equal to 20 square centimeters. And if we turn this up on its side, I'm going to kind of try that. So if we turn it up on its side, we find that let's see if this is out like this. We would have close to the water, we would have the water loving group, and then above it, the hydrophobic side. So those molecules are standing up on their ends, with one end attached to the water and the other end away from the water, dissolving in each other, actually. So that affords us the ability, since we know it's a monolayer, of saying how long is that molecule. Right? What we need to know is 3.23 times 10 to the minus 6 grams. That's the mass of the oleic acid. And all we had to do was, well, there are two ways you can do it. You can get your dropper and just make several drops, say 10 drops, weigh them, divide by 10, and that's how much a drop is worth. And then we find that the density of oleic acid is 0.895 grams per mil. This is the mass, and the density is equal to 0.895 grams per mil, which is the same as grams per cubic centimeter, right? Because 1 mil is a cubic centimeter. Okay, what's the question? What's the thickness of the monolayer, or what's the length of the molecule? Well, we have the area, and if we know the volume of this cylinder, remember the volume of a cylinder is area times height, right? So we know the area, and the volume equals area times height. We know the area, which is 20.0 square centimeters. If we can find the volume, then we can solve for the height, which is the length of the molecule. Okay, this is one of those problems that has to be broken down into several simple procedures. So we're looking for the volume of that thing. Well, as it turns out, density is mass over volume, right? And we have the mass and we have the density, so we can solve for volume. So the volume is going to be, let's see, move the volume over here and the density over there, equals mass over density. Did I lose anybody? If we say that density equals mass divided by volume, then if we move the volume over here and the density over there, that gives you this term. Okay, so now we have the mass, 3.23 times 10 to the minus 6 grams, and we have the density, 0.895 grams per cubic centimeter. Okay. Grams cancel. Remember, the denominator of the denominator is the numerator. So that denominator, cubic centimeters, flips up into the numerator when we resolve this term. And I get the calculator out. We can figure out what the volume is. 3.23 in exponent minus 6. Divide that by 0.895. I get, and since all of these operations are multiply or divide, I don't have to restrict my significant figures until the very end. Let's see, I got 3.6089 times 10 to the minus 6th cubic centimeters. Okay. So now I can put that value over here. If we solve for the height, it's volume divided by area, correct? Keep this one over here, that one comes over here. And this is volume 3.6089. 10 to the minus 6 cubic centimeters, and the height is 20 square centimeters. So that leaves us with centimeters, right? This square cancels two of those and leaves one behind. So the length is centimeters. So far, so good. Yeah, okay. Let's see, I've still got this one in my calculator. I'll just divide it by 20. And that gives me 1.8. And now we can restrict it to 3 significant figures. And I'll round it to that. 10 to the minus 7 centimeters is the height, or the length of the molecule. Now the units are in centimeters. So we would look for 1.80, which is D. Okay. So really, we've already covered density and how to use it. This is the one that you have to remember from geometry class. The volume of a cylinder, area times height. And drawing pictures helps a lot. I always draw pictures when I can. Question?
How did you, the centimeter squares of the centimeters cubed?
Oh,
Yeah.
yeah, this is centimeter squared is divided into centimeters cubed. Right? And this can be factored out as centimeters squared times centimeters, correct?
Yes.
So those two cancel and leave us with centimeters. Yeah, skipped a step. 57. WD-40 makes erasure so much easier. I could use this thing, but it just smears it. Kind of like the old chalkboards. You use erasers on the chalkboards. And eventually you have to take a wet cloth and just wipe them off. And then take the erasers outside and bang them on the wall. So 57. The density of gasoline is 0.7025 grams per mil at 20 degrees. When gasoline is added to water, what will it do? Well, actually, there's only one approach. The density of an object or anything that's placed in another object, liquid in liquid or solid in liquid, the object will float if its density is less than the substance you're putting it into. So the density of water is about 1, right? So 0.7 means that it ought to float. And your experience should tell you that too. Oil and water is always on top. So it'll float on top. That's a simple answer. Okay, 58. Okay, a piece of zinc with a mass of 12.14 grams. Mass 12.14 grams. Okay. And this is helpful also. When you read a word problem, everybody knows word problem's primary function is to confuse. They're written to confuse you so that we can weed out those who don't know what they're doing. Right? If you understand a problem, you can answer the questions, then there's no confusion. But if your mind is just off in left field, then any problem as written is going to be confusing. So what I like to do is extract the information and put it on the board in a form that looks familiar. It's submerged in 46.3 cubic centimeters of water. So the initial volume, and why do I say that? Because we're going to put that zinc in water, and it's going to change the volume. Initially, before we put it in, the volume is going to be that, 46.3. Okay. And then this graduated cylinder, afterwards, the level is going to be 48 centimeters. So final volume is going to be 48.0. Right. We're actually going to read milliliters on the graduated cylinder, but they're kind and they've already converted to cubic centimeters for us. The correct value for the density of zinc. So what we need is not this one, not that one. We need the difference. Right. So the difference here is going to be, excuse me, I've got it inverted. It should be this one, 46.3. 1.7 cubic centimeters. That's the change in volume. That's the volume that's attributed to this mass. And if we're going to calculate the density, then all we need is this formula. So we need 12.14 grams per 1.7 cubic centimeters. And the reason we want to put cubic centimeters is because we're doing the density of a solid. And by convention, solids density is reported as grams per cubic centimeter. And if we do our calculations correctly, we should come out with 7.1 grams per cubic centimeter. The other question is that a reasonable value? Well, let's see. This is almost 2, less than 2. So 7 times 2 is 14. It's less than that. So yeah, I'm happy. I didn't make any major mistakes. That's what we're looking for when we estimate things. All right, 62 coming up. The boiling of water is what? When we boil water, what's happening? Are we changing its identity? No, it's still water. It's just a different phase. So that tells me that it's either A or B, physical change. But why is it a physical change? Because that's the kicker here. Because the water merely disappears? No, water doesn't disappear. Right? It's still there. Right? We can't create mass and we can't destroy mass. That's a fundamental principle of chemistry. The gaseous water is chemically the same as the liquid water. That's the key for the answer B. All right. Let's see. Scroll, scroll, scroll. A lot of these are repetitions. All right. This is how many? We got four answers to do here. In order to do 70 through 73, we need to understand what these figures represent. These circles, dark and clear, or squares, dark and clear, or diamonds, dark and clear, represent atoms. Okay. So when we have a couple of atoms hooked together, like is in C, we have a molecule. We're talking about a molecule. When we have them separate, we're talking about a pure element like B. Okay. E would be a mixture. It's got molecules and atoms. We got a mixture of atoms in D. We have a mixture of atoms in A. Okay. So that's what we're trying to represent here. And that's the reason I put this one in our review, so that, right, some of these figures are not self-explanatory. So the first one, 70, which best represents a homogeneous mixture of an element and a compound. So we want one where we've got both elements and compounds together. And they need to appear homogeneous, that is, equal distribution throughout. And the one that looks best for me is E. Let's see, it's E. 71 wants to know which best represents gaseous compound. So what are you looking for in a gaseous compound? First, a gas, you're looking for lots of space between the particles. So that would either be A or C. The others are too close together. And then you're looking for a compound. That would be C, right? That's a small dark square and a large open. Small dark circle and large open circle. So C would be the best one for 71. 72 asks, which best represents a solid element? Okay, we want one with the same particles throughout, all the same. So D won't work, E won't work, C won't work, A won't work. Right. Well, we've already got C, that's a gas. We want a solid. Solid is very close together and regularly arranged. Right, so B looks like the best one to me. And the last one, 73, we want to know a heterogeneous mixture of two elements. So we'll go back up here, two elements, right? No compounds, right? So E and C are out, and A is a gas. We know that's always homogeneous. Any mixture between two gases is always homogeneous, no exceptions. So D looks like the best. Right? You've got a heterogeneous mixture. You see it's not uniform, but it has two different elements. Okay, so D works for this. All right, now we're going to 75. I'm going to use this. I clean it up later. Which of the following has a different value on the moon compared to Earth? Let's come at this one through the back door. Which one of these would be the same on the moon and the Earth? Mass, Well, time too, and moles also, right? They don't change. But the one outlier, the one that's not fit for being the same, is weight. Mass is a measure of substance, often measured as inertia. In other words, a resistance to movement or resistance to change in direction if it is moving. But weight is a force. And in this scenario, the force is based upon attraction between two bodies. Between, say, me on the surface of the Earth or the surface of the moon. They always said, I mean, you probably heard from the time you could watch TV, right? The difference between your weight on the moon and the weight, right? 1/6 on the moon. And that's weight. Weight changes based upon the objects that are attracting one another. You can actually measure the attraction between two balls, two, say, steel balls, set this far apart. And it has been measured. It's very small attraction, but they're two masses and they attract one another. That was one of the ways to prove that Newton was right. Actually, he was standing on the shoulders of Galileo, but that's the way things go. Which separation technique is based on the difference in the volatility of substances to be separated? Okay. Let's just take them. Let's see. The D. Yep. The first one, filtration. What's the difference we're looking at there?
Just the size of the particles.
Particle size. Yep. So that wouldn't be it, would it? That's not based on volatility. How about distillation? Yeah. Actually, distillation is based upon boiling point. Because you're taking a mixture of liquids, heating them up, and the one that comes off first is the most volatile. And then it comes off and the temperature remains constant till it's all gone. And then the added heat brings the temperature of the vapor up and it comes over. So we can separate them that way. There are complications, but that's the basic idea. So this is the one that answers that question. How about solvent extraction? We didn't talk about solvent extraction. Solvent extraction is a technique. I have two solvents and they don't mix with each other. But one of them has a compound in it that is soluble in both of them, only it's differentially soluble. And the mixture has different components. One is more soluble in this one than it is in this one. So we use what's called a separatory funnel. It's kind of like this, like that, and it has a stopcock at the bottom, and then it has a stopper at the top. And we put the liquids in here, and of course usually the organic one, the more organic one is on top. So let's put it like that. So this would be the organic one, and this would be the aqueous one, the water-loving one. Doesn't have to be water, but for examples. And what you have is differential partition between this. Let's just keep it simple. Two substances. One of them is more soluble in the organic than it is in the water, and the other one's more soluble in water than the organic. So, however they're mixed, whether it's organic or water, we put them together, and then we shake the hell out of it. We emulsify it, and then let it separate. And if they're colored, then you can actually see the color separation. One of them is going to be more soluble in water than it is. So it's differential solubility. That's solvent extraction technique. Sometimes you have to take this one and do it again, to get it fully extracted. It may not happen in one step. Okay, paper chromatography. We did talk about that one. So paper chromatography is based upon the differential attraction of molecules between a stationary phase and a mobile phase. So if it's more strongly attracted to the stationary phase, it's going to lag behind as the mobile phase moves through it. If it's more attracted to the mobile phase, it's going to move faster and they will separate. All right. Let's see. Now we're finally in chapter 2. Chapter 2. Okay, I'm going to have to move along really quick. 1, 2, and 3, these are... Okay, let's do 1, 2, and 3 together. You may have had to read your textbook to answer some of these. The first person to attempt to explain why chemical changes occur were the what? The Greeks. The ancient Greeks tried to explain why things change from one to another. They got it wrong, of course, but they did attempt. Right? I don't know if you've heard this. They used to most of the Greeks believed that everything was made of these four forces or substances: earth, fire, wind, and water. That didn't work too well. There were a few of them who,
I don't see the chapter 2 review.
it's in the same one.
It's in the same one? Okay,
Yeah.
got it. All right.
Yeah. Yeah, it's in there. There were a few who subscribed to the atomic theory, saying that everything was made of this elementary particle, the atom. They were getting closer. The problem was that they believed that everything was made of the same atom. And that's when they had to really do some mental gymnastics to try to explain why we have so many differences when everything's made of the same elementary particle. But they got the ball rolling. So that was the Greeks. How about the first chemist to perform truly quantitative experiments was? Now, we haven't talked about him much yet. It's probably buried in some small paragraph. Robert Boyle. Robert Boyle was the first truly quantitative experimentalist. We'll see Boyle again when we talk about gases. And then last, number 3, the scientist who discovered the law of conservation of mass and is also called the father of modern chemistry. I'll give you a hint, he was French. Lavoisier. Lavoisier proposed the law of conservation of mass. During a chemical reaction, the mass of the reactants is equal to the mass of the products. So that law being accepted, if your products weigh less than your reactants, you haven't accounted for everything. So that was what's E, right? E. Lavoisier. Lavoisier, he lived for a while during the French Revolution, and he had bought a tax contract from the king, which over a certain area of the country he could collect taxes. And when the king said, "I want this much," he'd give him that much, and everything else he got to keep. But you had to buy it, you had to pay for it. Well, that was okay as long as the king was in charge. But when the radicals got in charge, they went hunting for people they didn't like. The tax collectors were at the top of the list. So Lavoisier lost his head. Okay, number 4. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? The law of multiple proportions says, let's see, let's do a comparison. The law of definite proportions says what? Every compound has the same composition by mass of every element in it. And it doesn't matter where it comes from, what source. For instance, we could ignite hydrogen in oxygen atmosphere and collect the water vapor and determine its composition. Or we could purify water, right? Just reverse osmosis or distillation and ion exchange, get it as pure as possible. And you couldn't tell the difference between the two. They would be exactly the same composition by mass. That's the law of definite proportions. The law of multiple proportions says that when you have 2 parts to a compound, and it could be polyatomic ion or it could be an element, either one. Let's just, for argument's sake, say we've got A connected with B. Okay? The multiple proportion says that if, in the case where B and A can combine in different numbers, let's say we keep A constant and we can actually put 2 B's with it or 3 B's with it. Okay. The ratio of these B's to one another are whole numbers, right? So compared to the A in each one, This B is going to be twice the mass of that one. This is going to be 3 times the mass of that one. Okay. Now, at the time the law was proposed, they didn't know of the atomic ratios, right? They just knew masses. That the atomic ratios hadn't come yet. So we had to wait for Dalton to get that one. But those two laws are often confused by students. You get them mixed up. Definite proportions versus multiple proportions. And to answer the question, we have to have the same, if we're going to compare these two, we have to have the same elements or polyatomic ions in each one, right? So A wouldn't be right? It's got ammonium and ammonium chloride, right? That doesn't work. Or zinc and oxygen, zinc and chlorine, that won't work. Hydrogen and oxygen, hydrogen and chlorine, that won't work. Nitrogen and oxygen, nitrogen and oxygen. There's your ticket. Let's see, number 7. Oops, didn't mean to erase that. Second chapter. I think I need a new marker. Oh, it's getting too faint for my liking.
Sorry to interrupt you. I don't know if you can hear me.
I'm sorry.
Yes, I'm sorry to interrupt you. The classes that I've missed so far, are they also recorded just like this?
Yes.
Okay, perfect. I can
Yes,
go back and
yeah.
watch them.
Yeah, everything's in bright space.
Okay. Thank you.
Let's see, we're going to number 7. A sample of chemical X is found to contain 5 grams of oxygen and 10 grams of carbon. So this compound is 5 grams of oxygen and 10 grams of carbon, 10 grams. By now, these symbols ought to be becoming familiar, right? If you're doing your flashcard. 20 grams of nitrogen. Okay. So this compound has these mass proportions in that compound X. Right. That's Elon Musk's compound. He's got a fascination with X. I think he named his son X.
Something like that.
Okay, never mind. The law of definite proportions would predict that a 70-gram sample, let's see, this is 20, 30, 35, right? 35 grams total. That a 70-gram sample would have how much of carbon? Well, we doubled the total mass, right? So we have to double the amount of carbon. 20 grams. All right, number 9. Which of the following statements from Dalton's atomic theory? Oh, I guess that must have been from the chapter that I wasn't here. Okay. Yeah, because I don't remember doing it this semester. Yeah, chapter 2, right, is the one where I was absent. You had to look at the video. Okay. Dalton's atomic theory. Which one of these is no longer true? All right. Elements are made up of tiny particles called atoms. A, B, C, D, and E. That one's still true. Yeah. Atoms are not created or destroyed in chemical reactions. That's also true. Dalton says that they just swap partners, change places. All atoms of a given element are identical. No. What messes with that one?
Yeah, isotope.
Isotopes, yeah. Yeah, isotopes. Now, they're chemically essentially the same reactivity, but they're not identical. They've got different numbers of neutrons. Yeah. And then D, atoms are indivisible in chemical reactions. Yes, that's right. We don't break apart. It takes a nuclear reaction to break an atom apart. And then all of these statements are true according to the modern atomic theory. No, that's false. Okay, so C is the one. That's kind of misleading. E and C are kind of in conflict there. Well, like I always say, in multiple choice tests, pick the best answer. In this case, C is the best answer.
This is kind of off topic, but thinking of isotopes.
Uh-huh.
Whenever you have like, for example, like boron 36, like what does that mean again? Like in an isotope? I forget, I think it was in the video.
Boron what?
Like if you have like, if it'll be like boron and then it has a number, like it's talking about isotopes.
If it says boron 10
yeah.
or boron 11, those are probably the two of the most common isotopes.
And that refers to the neutron.
No, this is the mass number. When we write a symbol, just use that for a symbol. There are 4 places around that symbol for information. This is the place where we put the charge. Okay.
That might be wrong.
This is the place where, and if there's nothing there, then it's neutral. Or you can write a little 0 there if you want. This is the number of atoms that we're talking about. So like oxygen in the atmosphere is O2. Over here, this is the Z number or the atomic number. This is the number of protons. Okay. This is the A number or the mass number. And it's equal to the number of protons plus the number of neutrons. Okay. So if you have both of these numbers, you can calculate the number of neutrons and just subtract this one from that one. And that's what these numbers are. Mass numbers. Mass numbers are always whole numbers because they represent a summation of the number of protons and the number of neutrons. The atomic mass is this number. It's a weighted average of the masses of the various isotopes. So if the abundance of isotopes is weighted toward just one, then it's going to be very, very close to a value with a small, let's see, example. Like this carbon. Right? Most of carbon is carbon 12. Right? Carbon 13 will bump it up a little bit on the weighted average. It's like calculating a grade point average. Right? An A in a class with 4 credit hours is worth, on your average, is worth more than an A in a 1 credit class. Right? And that's the same idea we're using here, weighted average. Okay. Let's see. The chemist credited for inventing a set of symbols for writing elements and a system. Let's see. I need to uncover that so I can read it. A system for writing the formulas of compounds and for discovering selenium, silicon, thorium. Right. I hope I covered that in the video. This is Berzelius. Berzelius was a Swedish chemist. And there were a number of different systems that had been proposed for representing the elements. Dalton proposed one that was derived from the alchemists. The alchemists had these weird set of symbols for the elements, and that would have been a nightmare. Berzelius had a better idea. Let's just use the first and the A second letter for each one, right? And the earlier ones, the ones that came along first, got dibs on just a single letter, like boron, carbon, nitrogen, oxygen, fluorine, right? And then the ones that came along after, if they had the same first letter, we just had to add a second small letter. Like instead of C, we have Ca for calcium, Co for cobalt, Cs for cesium. Okay, the second letter is always small. But that was Berzelius' idea. Avogadro's hypothesis. Avogadro's hypothesis states that at the same temperature and pressure, equal volumes of different gases contain equal numbers of particles. It's just that simple. I hope in the video I showed you 2 volumes of gas. Yeah, we talked about that. Okay. Avogadro's hypothesis was the basis upon which a serious problem was resolved for both university-based chemists and for company chemists. Because up to that point, up to the late 1800s, reactions were viewed as mass combinations, right? Mass of this reaction, mass of that reaction. When something went wrong, they had no clue how to fix it because they didn't understand that reactions are not mass. They're numbers of atoms, numbers of molecules, moles. That's what dictates the reaction and the outcome. So Avogadro's ideas contributed to it, and then one of his students, Cannizzaro, is the one who popularized it. And in fact, Mendeleev credited Cannizzaro in his publication of his periodic table as helping him to resolve issues with where he put elements in the table. The first scientist to show that atoms emit any negative particles, 13. J.J. Thomson. Remember, he studied the negative particles, identified electrons as emanating from every element. So they were subatomic particles that were common to all elements, electrons. All he was able to do was to determine the mass to charge ratio. It wasn't until, and my mind's gone blank. It wasn't until, I'm sorry?
Was it the wheel draw?
Yes.
Millikan?
Millikan, thank you. Yeah, Millikan used the results of Thomson's work with his oil drop experiment, and he gave us the mass of an electron. Okay, 14. Many classic experiments have given us an indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Okay. Rutherford's experiment proved Thomson's plum pudding model. Nope. It put Thomson's plum pudding model in the trash can. Rutherford's idea was the nuclear atom with protons. Actually, at the time he did the experiment, or his assistants did the experiment, all they knew about were positive and negative charges. And the positive charges in the plum pudding model were scattered. They were diffuse. And then they didn't even consider them particles, but they knew that the charges had to balance. Rutherford said that those are actual particles, and that's where most of the mass is concentrated in a small nucleus. Once he proved the nuclear model, then he set his research assistant, let's see, Rutherford and mine's gone blank again. Said his assistant on discovering how do we account for that extra mass? Because the protons didn't account for all of the mass of an atom. So, I think his name starts with a C. Chadwick. Chadwick discovered the neutron, proved that the neutron existed, and that accounted for all the mass of the atom. And both Rutherford and Chadwick got Nobel Prizes for their work. The Rutherford experiment determining the nuclear charge on the atom, Millikan's oil drop. Well, the rest of them are true. A is false. The scientist whose alpha particle, well, we just said that. Ernst Rutherford was the used alpha particles fired at gold foil to prove his model. Some of these, the word that we like to use in the sciences for these types of experiments is elegant. They're so simple and they answer huge questions. Um, 16. Alpha particles beamed at thin metal foil may what? Well, they can pass directly through without changing direction. Yep. They can be slightly diverted by attraction to electrons. Yep. Alpha particles are positively charged, so they're going to interact with the negative electrons. They can be deflected by direct contact with the nucleus. Yeah, all three. We saw that in Rutherford's experiment. 17. Which one of the following statements about atomic structure is false? An atom is mostly empty space. That's true. Almost all the mass of an atom is concentrated in the nucleus. Yep, that was good too. Protons and neutrons in the nucleus are very tightly packed. Oh yeah, very tightly packed. And that brings up the question that has to be answered later. If you put positive charges that close together, what do you expect them to do? Fly apart. Yeah, they repel one another. So we think that that's why the neutrons are there. They're there to stabilize the protons. And we find that the more protons you get in the nucleus, the higher the ratio of neutrons that are required, because the strong nuclear force acts over a very, very short distance. So you've got neutrons in this area working on these protons, but over here, they no effect. Right, so you need a lot more. Up until you get in this region, the ratio is essentially 1-to-1, one proton for every neutron. But as you get heavier and heavier, you need a lot more neutrons. And they believe that there's an exchange particle between the neutrons and the protons. So it sends it over to the proton, the neutron becomes a proton, and the proton becomes a neutron. Anyway, the number of protons and neutrons is always the same in the neutral atom? No. Right, we have isotopes. Right. So D is the one that's false. Okay, let's clean that up and go to number 20. I know I'm going to run out of time. Sad. Which of the following atomic symbols is incorrect? Well, the first thing I would do is I would say, all right, the symbols represent carbon, chlorine, phosphorus, potassium, and nitrogen. Then I would look to the periodic table and say, all right, where's the atomic number? It's in the lower left hand of each symbol, right? So is 6 carbon? Yep. How about 17? Is that chlorine? Yep. Phosphorus, 15? Yep. Potassium, 19? Yes. Nitrogen, 8? It's 7. There's your bad boy, nitrogen. Because elements, the element name, the element symbol, and the number of protons are joined at the hip. If you change the number of protons, you've changed the element. So 8 for nitrogen would not be, it'd have to be oxygen. 21. The element rhenium, and that's not one that I had you memorize, exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus so many protons and so many neutrons. So this is a little tricky. Find rhenium, which is right here, 75 protons, right? So A, B, D would be potential answers. But we need the number of neutrons. So if you're looking at the periodic table and you see rhenium-186, where do you go with that? Because that's not a whole number. Well, the closest whole number to that, and the most common isotope, is probably rhenium-186. So you take 75 from 186, right, and you get, well, that didn't work. Did I read it right? Yeah, 186. Oh, wait a minute. 2 stable isotopes. Oh, 185, excuse me. It says rhenium-185. So there you go. 75 from 185 is 110. Okay. I wasn't taking advantage of all the information that was given. So D is the best answer for that one. 22. Which among the following represent a set of isotopes? In order to have a set of isotopes, and we're picking from Roman numeral 1 through 5, you have to have the same number of protons. So how about 1 and 4? They have the same number of protons but different number of neutrons. So 1 and 4 is a good choice. That's a set of isotopes. 21 would be 2 and 5. They have the same number of protons and different neutrons. So 2 and 5. And then 3 is left out in the cold. It's all by its lonesome. So there are no isotopes of that one. So we only have 1 and 4, 2 and 5. That's D. Come on. Go skip a few. 28 and 29. A species with 12 protons and 10 electrons. Okay, if we have 12 protons, that's where that goes. But if we only have 10 electrons, what's the imbalance here? Charge. We have 2 more positives than we do negatives, which means a 2 plus charge, right? So whatever this X is has a 2 plus charge. And if it's got 12 protons, we're looking at magnesium, right? Magnesium with a 2 plus charge. Okay. 29. The number of protons, neutrons, and electrons in potassium 1939. Potassium 1939. So there's the number of protons, right? The number of neutrons would be 39 minus 19 is 20. Right? How about electrons?
Less.
So that'd be 18, right? 18 electrons. Because you have 1 excess positive. Yep. That would be E. Best answer for that one. Okay. Now this is testing your ability to associate symbols with names of elements. I'm not going to put those up there because this is just, you got to know them. 33, which of the following are incorrectly paired? Well, this one is groups, excuse me. I'm getting ahead of myself. This is groups, which is strontium is in that alkaline earth. Yep, it's in the second column. Strontium is an alkaline earth. How about tantalum, transition metal? Let's see, Ta. I don't think I had you memorize that one. Ta, yes, Ta is number 73. It's a transition metal. That's good. F, is that a halogen? Oh, yeah. H, hydrogen is not a noble gas. No. I bet the Hindenburg crews wish that it had been. Right? Right. Hydrogen in the Hindenburg, because all it took was a little spark and it just went up. No, it was lickety split. And ruthenium is transition metal. Yeah, Ru is over there at 44. So D is the bad one. Hydrogen is not a noble gas. Add a little E after that, and you're good to go. Right? Helium. By the way, where was helium first discovered? The atmosphere of the sun. It was discovered spectroscopically. And of course, it was named helium because that's where it was found. Helium is Greek for the sun. Helios, actually.
Then they said, hey, let's put this in a balloon.
I'm sorry?
Then they said, hey, let's put this in a balloon.
Yeah, right. And then when we do that, well, let's breathe some of it and see what happens. And talk funny. Okay, 34. Which of the following are incorrectly paired? All right, first one, phosphorus. Is PR phosphorus? No. PR is way, way down here. I think that's protactinium. So that one's wrong. And if you're in a hurry in a test, we found the wrong one, let's move on. The rest of them should be correct. 35, which of the following are incorrectly paired? All right, is Cu copper? Yep, cuprum, Latin cuprum. Carbon? Yep, that's good. Cobalt? Yep. Calcium? That one's good. Cesium? Nope. Ce is cerium. Cs is cesium. So cesium is in the first column. Cerium is, I think it's down here somewhere. No, where is cerium? Get a reflection.
See, it's down in the lanthanides on the first.
Yeah, there it is, 58. Yeah, cerium. 36. Antimony. SB. Yep, stilbium. Silicon. Yep, that's good. AG for silver. Yeah, argentum, silver. Argon, AR. That's good go. Astatine. No. AT is astatine. AS is arsenic. Okay, 37. All the following are characteristics of metals except good conductors of heat. Good. Malleable. Yep. Ductile. What's the difference between malleable and ductile? Malleable is moldable. Right? Ductile is you can stretch it into a thin wire. Based upon the same characteristics, but it's a different word. Often lustrous. Key there is often. Metal that's very, very finely divided, small particles, is black. It's only when you accumulate a significant layer of those metal atoms that you get the shine. And tend to gain electrons in chemical reactions? No, that's nonmetals. Metals tend to lose electrons. Okay, 41. You're given a compound with the formula MCl2. M is abbreviation for metal. Right? You're told that the metal ion has 26 electrons. 26 electrons for that metal. What metal is it? Okay. If this is an ionic compound, metal, nonmetal, we know the charge on chlorine in ionic compounds. It's -1. So that means it contributes a -2 total. That means this one metal ion must be +2 to balance. And if it's +2, then it has 2 more protons than electrons. Now we can go to our periodic table. 28 is nickel. So this one is nickel. Okay. Let's see. How about 45? How many oxygen atoms are there in one formula unit of calcium phosphate? All right. Correct? Yep. Now, why can we write it that way? Because we know that calcium is always 2+. And we know that phosphate is a polyatomic ion with a fixed charge, 3-. So to balance them, we cross multiply. 3 comes over here, 2 comes over there. And check yourself, like 3 times 2+ is 6+, and 2 times 3- is 6-, so it balances. But now we want to say how many oxygen atoms are in that formula. This parentheses means that this 2 multiplies everything inside. So we have 8 oxygen atoms. All right, now we're going to check our ability to name compounds. 47. The correct name for FeO. First, non-metal, nonmetal, or metal, nonmetal? Metal, nonmetal. So it's either a 1 or a 2. Okay. Can iron assume more than one charge in a compound? Yes, it's a number. It's a number 2. So we have to say what the charge is. So that means we've got to deduce what the charge is on that iron. We know that oxygen, right, chalcogens are all 2-. So that means this is a 2+. So we would say iron 2 oxide. There you go. Now, when I was a student, they still had the old system. We had us and ick endings. So this would be ferrous oxide. And you just had to know what the charge was based upon that, because us is in some other element might be a 3, or it could be a 4. So they fixed that problem. We just use Roman numerals now. 48. The correct name for Ca2+. Okay, the temptation here is to put the Roman numeral in. But calcium is an alkaline earth, and all alkaline earths are 2+. Remember, the 2 rules guiding our nomenclature are unambiguous. In other words, once you've got a name, it says this is the compound written correctly, or the compound says this is the name. There's no other choice. There's only one option for going either way. And the other is non-redundant. If we said Ca Roman numeral 2, that's redundant, because Ca2+ is always calcium ion. Okay? All right. So that's C is the answer for that one. 51. Let's see. What's the subscript of barium in the formula barium sulfate? Let's see. Where's barium located? Barium is an alkaline earth. Right? So it's always 2+. And sulfate is a polyatomic ion. is always 2 minus. So what's the subscript? It's the one that we don't write, right? We don't write a 1, but it's understood to be 1. Right? That would be redundant. Because if the symbol's there, there's got to be at least one of them. So if you don't write a number, we assume it's 1. All right, 53. 53. So we're going from the name to the formula. Sodium dihydrogen phosphate. Sodium is an alkali metal. It's always a +1 charge. So just to keep it straight, I'm going to put the charge in there. Hydrogen phosphate is this, right? It's a 2 minus. If you don't want to have to just plain memorize stuff, just say, oh, excuse me, it's dihydrogen phosphate. My mistake. Dihydrogen phosphate. So if phosphate is a 3 minus, and you add 1 hydrogen, now it becomes 2 minus. If you add 2 hydrogens, there's another hydrogen to that one, then it becomes 1 minus. So the hydrogen takes away a charge each time. Okay, so the formula is just that. Sodium dihydrogen phosphate. A. About 56. What are we getting into here? Acid nomenclature? Yeah. So we have aqueous solutions of each one of these acids, which is incorrectly named. All right, H2SO4. If it has an oxygen in the formula, we don't say hydro, right? Leave the hydro off. You go straight to the polyatomic ion because that's where the oxygens are going to be. And we look at sulfate. And we say sulfate, H's become X. So 8 becomes sulfuric. First one is good, that's true. CO3, there again, carbonate ion, H become X, carbonic acid. PO4 is phosphate, phosphoric acid. A, B, and C are good. HCN, there's no oxygen there, so we have to say hydro. It should be hydro, and the cyanide, I becomes ic, hydrocyanic acid. So D is wrong. The last one, hydrochloric, is correct. Ics become, Ides become X. Hydrogen chloride, if it's a gas. Dissolve it in water, then we have to name it as an acid.
That's because of oxygen or
The lack of oxygen, we say hydrochloric. Which of the following names is correct? Right? So that's 59. Sulfide. That looks good. Yeah, sulfide. Ammonium chloride. Yep. Ammonium is a fixed charge, so it fits into the number 1 category, Roman numeral 1 types. If the species occupying the metal position is a fixed charge, then we treat it like a type 1 compound. Right, so ammonium chloride is correct. C2H3O2. C2H3O2 is the acetate ion. It's a polyatomic. So we don't say hydro. We know it's an acid because the first element is a hydrogen. Now it has other hydrogens in there, but they're fixed. They're locked in place. They cannot contribute to acidity. It's just that first hydrogen. And it can either be 1, 2, or 3. I've never seen 4 hydrogens in the name, but it could be. And the acetate, 8 becomes ic, we just say acetic acid. And that's the compound that you find in vinegar. 5% acetic acid is vinegar. Barium oxide. Barium is a fixed charge metal, right? 2 plus. Oxide, we only have to say barium oxide, that's it. 1 barium 2 plus, 1 oxygen 2 minus, they're balanced. So all of them are correct. Lots of practice required.
So barium oxide is a type 1, correct?
Correct.
And so if, say, the formula said like BaO2, it would still be barium oxide?
No, it would be wrong. It
Okay.
can't be,
Okay.
right? BaO2 says that oxygen with a 2 minus charge times 2 is a 4 plus, a 4 minus. Barium would have to be a 4 plus. That's wrong.
Okay.
Yeah. Now, if we put something with a 4 plus charge possible, let's see, maybe silicon. SiO2 would be, that would be good. Yeah, that's sand. Okay, fill out this table. All right, I'm about out of time. The way to fill out this table in 61 is the red letters and the blue are what we fill in. So we've got PB with a 206 in it. We know that lead, we have to go to the periodic table. So lead is going to be 82 protons. Right? So that's what we put in there, 82 protons. There's no charge, so there's 82 electrons. And the net charge is 0. And then we just subtract 82 from 206 and we get 124 neutrons. That's how you fill it out. What do you have? And then you go to answer the questions. Gallium, look it up. Gallium is 31 protons. We're given that, excuse me, 31 protons, 38 neutrons. So that means that since it's a 3 plus charge, then the number of electrons must be 3 less than the protons, 28 instead of 31. Tellurium 2 minus, we put the 2 minus charge out there on the far right-hand side. Well, actually, we couldn't put gallium in there because it needs to be filled in. So we have to go to the 31 protons. And then we calculate the number, and the net charge is 3 plus. So Ga3 plus is derived from that information. Tellurium, we have to go to 52 protons. Right, 52, yeah, tellurium. It's a chalcogen. And then the charge, we have to calculate the charge. We compare the number of protons and the number of electrons and find that we have a 2 minus, 2 electrons extra. So that's a 2 minus charge. And then, let's see, manganese 2 plus is given, charge is 2 plus given, neutrons is 30 given. So the number of protons is, manganese is 25. You have to look at the periodic table, find 25. And then with manganese 2 plus charge, that means we have 2 less electrons, which is 23. And that's how you fill that out. And you follow a similar logic with 62. Now here we want to silver, Ag, calcium, Ca, iodine, I, capital I, copper, C, small u, phosphorus, P. Name the compounds. Right. 64A is a type 2 compound, so the iron must be given charge. Sulfate is a 2 minus charge. Iron then must be a 2 plus charge. So iron 2 sulfate is correct. Acetate, C2H3O2, is a polyatomic ion. And sodium is always a +1 charge. Acetate's always a -1 charge. We just need one of each, call it sodium acetate. And it's a type 1, so we don't have to say the charge because sodium is fixed. Potassium is fixed, and NO2 is nitrite. We balance the charge. Potassium is +1, nitrate's -1. If you like bacon, you've probably eaten nitrate. Unless you get that uncured. Right? That's popular now. I don't like it because it doesn't have the flavor. It's just bland. Must be the nitrates or the nitrites that give me the flavor. Calcium is a fixed charge, so it's a type 1. Hydroxide is a polyatomic ion with a -1 charge. So we need 2 hydroxides, which means parentheses. Okay. Polyatomic ions, if you need more than one of them, you have to use a parentheses. You can't change the subscripts. You have to have a parentheses, then you put a subscript outside the parentheses. Because that charge on a polyatomic is not assigned to any individual atom. It's for the whole group. So we have to encase it in parentheses in order to express that multiple negative or positive charges. Nickel, that's a transition metal. It has possible multiple charges. Carbonate is a 2- charge. Nickel must be a 2+ charge. So we have to put the Roman numeral 2 in there. All right, we're naming compounds here. That one's kind of slid off the top. Nitrate ion should be NO3-. Aluminum oxide. Aluminum is a fixed 3+ charge. Oxygen is a fixed 2- charge. You just cross multiply. Al2O3. That gets it. Ammonium ion, NH4+, that's good. Perchloric acid. Perchloric means we're working from ic comes from 8. So perchlorate ion is ClO4. Right? I think in the video, did I describe a homologous series of polyatomics like chlorate, perchlorate, chlorite, and hypochlorite? Okay, so this would be the 8, this would be the ite, and then we have to use a prefix, hypo underneath the ite, and per above the 8. And this works for bromine, right? It'd be perbromate, or it works for iodine, periodate. So that way you can, I mean, if you know the sequence, you can memorize like 12 of them just like that. And copper 2 bromide. Copper has the potential for multiple charges. Bromide is a -1 charge, but we know that copper is a 2+ charge. That means we need 2 bromides, CuBr2. Okay. And here's a whole list of them. Right, just follow the rules. Yep, I'm past due. See how much I have left. More, write the formulas. And then we have these, we talked about law of definite proportions already. Law of multiple proportions. Which of these does not have a Latin derived name? Right. FeCuNak, titanium. Titanium doesn't have a Latin derived name or symbol. Which of these is not likely to form from the appropriate atom? Look at the group that they're in. And you can also look at, on your periodic table, those lists of charges. Right. First couple of charges, they're bona fide charges. The rest of them are usually oxidation states. And we haven't talked about that yet. Those are not bona fide charges. Let's see. You can figure that one out. Naming correctly. Right, this is just going to take practice. And since I didn't go over those in detail, if you need detail, go to a previous semester where I had time to finish and look at the end of the video and you'll see these described in detail.
Oh, we have access to videos from previous semesters?
Oh, yeah. Look under, with each one of the modules for exams, module 1, 2, 3, 4, exam 1, 2, 3, 4. They'll have inside a module inside that module will be called archived videos.
Okay.
And you can go look at ancient videos. Most of them have a dozen or more, but they're in chronological order. The most recent one is at the top. So just go to the closest one, and then you'll be able to scroll down and finish what I didn't finish today.
One more question, since we do have,
Yes, ma'am.
since I just joined so late, we do have that exam on Tuesday. Your advice for getting through that exam, read the first 2 chapters and go over this review. Is that like the best things to do to pass
Yes.
that exam?
Yes.
Is it, 'cause I'm still getting oriented to the bright space. I will be cramming this weekend, but I'm just a little bit worried because I'm jumping in and there's an exam on Tuesday.
Yeah. If you're pressed for time, just go to the review document and be
Okay.
sure you understand each one of these questions.
Okay.
Think about how the question was answered,
Okay.
because I could take one of these or several of them and just tweak them a little bit.
Okay.
And that'll test whether you understand how we got the answer in the first place.
And then one more question, this
Okay.
document, that's the exam review, do we have the key as well as a blank one so that we can do our own work and then check it?
Yes.
Okay,
The
perfect.
key is in Brightspace.
Okay.
And then there's another document called worked problems.
Okay. Okay.
It's in there with it, and I work out the problems by hand.
Okay.
If you get stuck, then go to the work problems, and it should help you understand how I answer that question.
And it's only the first 2 chapters that the exam is over. There's no further content beyond those 2.
Correct.
Okay, perfect. Perfect.
Yeah.
Thank you so much.
Okay. All right.
All right.
Well, we're done.
Okay.